Did I start the recording? Yes, I did. Okay. Why is it not loading yet? I mean, it should. Oh, that's the reason why. Oh, and the picture's muted. That's why. Weird. Okay. All right. So, there it is. Okay. Mouse. Okay. So, we're gonna continue on where we left off. Um, I guess I forgot to write unit. I just wrote unit, not unit one. Or maybe I pressed the back button, but either way. I just wanted to kind of give you a rundown of the final exam. It's probably going to be around this spread, about 20 to 30% on unit two, 20% unit three, 20% unit one, and about 30% unit four. So more emphasis on unit four than the other ones. That's kind of to be expected. It's the more fresh material. Um, and then, I mean, like technically speaking, you could probably say that about 50% is unit two material because unit three requires you to know how to do unit two, right? You can't really do applications of derivatives unless you know how to take a derivative. So that's a good rundown. And as a usual rule of thumb is that you should be looking for the main cruxes of everything. Do you know how to take a general derivative? Do you know how to use the product rule, quotient rule, chain rule, and all that stuff? Do you know how to find the critical points, the critical values of a function and determine where it has relative extrema? We're not looking for can you find a slant asymptote, sketch the graph situation. I'm not sure why my computer or my iPad disconnected here for a second. It's still connecting. We'll see what happens. I should be still recording. So yeah, uh, give this a second. No worries. Um, where was I? So yeah, that's gonna be about the rough breakdown of everything. Does anybody have any questions while we're waiting for this thing to reload? Perfect.
For the exam?
Yes, for the department exam. And as a reminder, the department exam is has its own requirements. Uh, my iPad is not connected. I'm going to pause it real quick. Let's see. Let's see.
No.
Okay. Now we're back in business. So yeah, that's probably going to be a good rough estimate of what you can expect on the exam. As I said, like meant to be an overarching view of your knowledge. Now, in the interest of time, I'm going to skip this example, but I'd encourage you to do it on your own time, setting up the integral for the area under the curve y equals x squared plus 2 from 0 to 3, essentially, is what that would be. I want to spend more time on this one here. Consider the region bounded by the curves y equals 2x plus 3, y equals 0, x equals 1, and x equals 4. Find a constant b such that b splits this region into two parts of equal area. Okay, never done this before. But as soon as we see that we're trying to calculate the area of a region, we should draw a picture to try and help us out. So let's go ahead and visualize this. Y equals 2x plus 3. That's a line with slope 2 and a y-intercept of 3, right? So here's 3, and it does not need to be drawn to scale. In fact, sometimes that actually ends up causing a little bit of problems because sometimes these curves grow very, very quickly. But this is y equals 2x plus 3. Just, we don't need to worry about scaling too much because we're not trying to find out specific values, really. We're just trying to visualize the region for a second. So that's one of the bounding curves. The other one is y equals 0, so the x-axis, the flat line, and then x equals 1. X equals 1, and x equals 4. And we're trying to find a vertical line x equals b that splits these things up into a perfect region. So here is line B, or x equals b, and we want the area of region 1 to equal the region 2. That's what we want to do, right? Let's make sure we understand it and visualize this picture one more time. The blue line is the line in question, y equals 2x plus 3. The region, the total region bounded for a second, consider the region bounded, that's this entire area. That would be the region bounded by 2x plus 3, x equals 0, and y equals 0, x equals 1, and x equals 4. We want to find a line B that splits this region into two equal pieces. So what we are trying to do, we want the area of 1 to equal the area of 2. That's what we want. That's like, so what I'm doing right now is I'm trying to write the problem statement from English into mathematics. And sometimes that can help me gather more information. So I want the area of region 1 to equal the area of region 2. What's the area of region 1? We're going to need to use integrals. And it's that first piece. So it's the area under the curve. The good news is our function is above the x-axis, so the area, the actual area and the area of the curve coincide. So it's under the curve 2x plus 3, so that's going to be our integrand. That's going to be the thing on the inside of it. So 2x plus 3 dx. What are the bounds then? 1 and b. For region 1, it goes from 1 to b. And the area of region 2, it starts at b and goes to 4. So now we can compute it. Yes, b is like, it looks a little bit weird, but remember, b is just a fixed number, some number between 1 and 4. We don't know what it is. It could be a nice number. It could be an irrational number. We don't know. But we'll go ahead and compute these things. So the integral from 1 to b of 2x plus 3 dx, well, that would be, find the antiderivative. The antiderivative of 2x would be x squared. Antiderivative of 3 would be 3x, evaluated from 1 to b. And that would be b squared plus 3b minus 1 squared plus 3 times 1, which would be b squared plus 3b minus 4. That's the first one. Now I want you guys to find the second one. I want you to find the area of region 2 in terms of b. And what's cool about this problem, by the way, so I actually gave this on one of my exams as an extra credit problem a long time ago. And one of my students actually ended up like they were able to finish the exam early, and they went and proved this in 3 different ways. They used geometry for one of them. They used this method that we're doing, which is what I would think would be the most intuitive one. Maybe I'm wrong. And then they did another integral proof as well. So there's many different ways to do this. So continue working. Equals 12, 28. You got a calculator? You should get negative b squared minus 3b plus 28. I mean, you could write it as 28 minus b squared minus 3b. It doesn't matter, but we need these equal. Because we want the area of region 1 to equal the area of region 2. And that's good news. That's a polynomial equation. So we've got b squared plus 3b minus 4 equaling negative b squared minus 3b plus 28. It's a bad 3. And then we bring everything to one side just like we know and love to do. So we'll add the b squared, add the 3b minus the 28. We get b squared minus or plus 2b squared plus 6b minus 32 equals 0. And you can try and factor it. I don't think that it factors nicely by the looks of it, just based on that alone. It was 72 and 64, two numbers that add like that multiply the negative 64 and add 6. I don't know. It doesn't matter. I'm just gonna use the quadratic formula. Does it not have nice roots? Probably not. So by the quadratic formula, b is equal to negative b, so negative 6 in this case, plus or minus the square root of b squared, so 6 squared, minus 4 times a times c, which is negative 32, all divided by 2a, so 2 times 2, which is, let's see here, negative 6 plus the square root of 36 minus 4 times 2 times negative 32, all over 4. I get b equals approximately 2.77 and then negative 5.77. All right. So one of those is not, like, there's two different choices. One of those is not correct. Which one? The negative 5.77. That, like, granted, actually, technically speaking, I never said that the b value had to be between 1 and 4. But the correct answer would be 2.77. Now, let's visualize why negative 5.77 would still work. Why is that the case? So remember, this curve will continue downwards, right? And over here is negative 5.77. So you don't need to draw this. But basically, if I divide them up, if this is my b value, then the area of the region 2, let's use green for a second. The area of region 2 is everything here. So it has to, like, it ends up adding some negative area. Then it might seem weird. It might seem weird. How does the area, so that's the area of the region 2 in that case, and region 1 would be this. But remember, you're integrating from 1 to b. So it looks like it's going to be, like, it's probably going to, like, now my graph is not drawn to scale, but it looks like it shouldn't be as nice. Mostly it's because of the fact that my integral is, like, my drawing is not drawn to scale. This thing would actually go a lot further down. But because we're integrating from 1 to b, and b is less than a, b is less than 1 in this case, the area will be double negated, like because you're adding negative width rectangles. But either way, I'm getting a little bit sidetracked. So the answer is that both of them technically work. It's just for different reasons. So want 1 less than b less than 4. So b is equal to 2.77. Isn't that cool problem? You can find out how to split a trapezoid completely in half now. It's a super useful thing that we can do in our daily lives, right? Victor, you've done that a bunch of times in your daily life, right? Having to split up a trapezoid into 2 equal pieces.
Yeah.
Perfect. I knew it. I knew it. Okay. The next thing, unless there's any questions on that one. Definite integrals and absolute values. So as a reminder, the absolute value function, what it does is it takes anything that's negative and flips it to positive. That's the practical application of it. There is a lot more mathematical intuition that comes with the absolute value when you think about it as the distance from zero. But regardless of that fact, what it does is it takes all the negative portions of the function. So remember, f of x is a function value. It's a y value. So it's going to take all the y values and flip them upwards. So as I said up here, basically it takes any piece that was negative and reflects it across the x-axis. So this is the function f of x. The function absolute value of f of x looks like this. This is y equals the absolute value of f of x. So I need to find out the, I need to do the integral from 0 to 5, right? So I want the area of this region in question, 0 to 5. So that's going to be split up into two pieces, right? There's this piece and this piece. Now, the graph is given to us here. So we already know that we just need to split it up based on 3. However, what if we weren't given the graph? First and foremost, we need to know where it equals 0 so we can find out where the function is positive and where the function is negative. So if graph not given, you're going to set f of x equal to 0 to find out where its critical value, or its what I used to call VIPs in Math 126. We want to know where the original function f, not the absolute value function, we want to know where the original function is positive and where it's negative. So setting 3 plus 2x squared minus x squared equal to 0. We get 3 minus x times 1 plus x equals 0. That gives me x equals 3 and negative 1. So those are the places where the function will switch. Hypothetically, it might bounce, right? Some curves end up looking like this, right? They go through and then they bounce at a 0. So we need to make a sign chart now. So make a sign chart for f. Here is negative 1. Here is 3. All right, so let's recap while people are still writing, because I did write that quickly. We're setting it equals 0 because we're trying to find out where the curve might go below the x-axis. Now, so now that we know where the zeros are, now we can create a sign chart to figure out where the function is positive and where the function is negative, so that we know when to tack on an extra negative sign. JD, you have a question?
Sorry, we're just doing all this and like the idea of not having the graph to look at. Right?
Exactly right. So normally, like right now, we're given the graph, but what if we weren't? What would we have to do? So we'd have to find the sign chart, x equals -2, x equals 0, and x equals 4. And as you might guess, you get negative, positive, negative, as we see above. So, I mean, feel free to test them out. You'll get over here, you get a positive times a negative, and you get a negative times a positive times positive, and then you'll get a negative times positive, and it'll give you the three different signs that we decided upon. So the area of the region, or let's say area total, equals the area of region of area of 1 plus the area of 2. Now, area total, that would be the integral from 0 to 5 of the absolute value of 3 plus 2x minus x squared dx. That's the area of the total. And that's okay because that is definitely a function. Yes, yes, I'm aware that my battery life of this thing is non-existent. That does actually represent area because the absolute value function is always above the x-axis. So if we were able to find what the antiderivative of this function was as an absolute value, you can't really do that. I mean, there's ways around it, but regardless, then you probably would be able to figure this out. But we really just need to split up into two pieces. So the area of the first piece, from 0 to 3, we are positive. So our function and our absolute value function coincide. So this will be the integral from 0 to 3 of 3 plus 2x minus x squared dx, plus the integral from 3 to 5 of negative the quantity 3 plus 2x minus x squared dx. Because for the piece between 3 and 5, the original function is negative. But we're dealing with the absolute value function. So what we have to do is on that piece, we just need to tack on and we need to multiply the entire function by -1 to reflect its y values to make them positive. Any questions on that? Now I'm going to skip doing the next part of it, but what you'd want to do is you need to find the antiderivatives, evaluate them at the endpoints, take the difference, capital F of top minus capital F of bottom, and go from there. Any questions on that? Now, so remember how constants work too. You could, in theory, distribute the minus sign through. You could definitely do that. You could take this negative sign and go through and call it good. That would work. In fact, maybe we should do this. Or remember that constants can be brought out front of integrals. So what you could do is you could then just take this -1 and put it out front, right? Because it'll be plus a -1, which is really subtracting. Either way, no matter how you slice it, you'll get the right answer. It's your call. Most people like to do it this way, but that's fine. And then we get our answer, which I don't. I'm just gonna jump around though, because I don't want to spend too much time on this when we have bigger fish to fry. Do I have the answer right off the bat for us to look at? Yes. 59 thirds. Equals 59 thirds. So if you don't get that answer, you should definitely be practicing this because it's going to be on the exam, these types of things. Maybe not the absolute value thing, that seems a little niche, but knowing how to do the definite integrals, from this point on, you should be comfortable doing this calculation. Maybe going from here to here, maybe not so much, but in general, you should be able to handle this. If you can't, that portion of the exam is going to be problematic for you. So, yes.
What's the sign chart?
The sign chart was to determine, so we were given the graph. And so we knew what the absolute value function would look like based on the fact that any of the negative pieces become positive. But if I didn't give you the graph, it would be very, very difficult to know which piece is above the x-axis and which piece is below. So the sign chart was there to help us figure that out. So that's one of the things that I spent a lot of time in my not a lot of time. I don't have enough time in 126 for anything. But I make sure I mention that when it comes to a sign chart is more than just solving inequalities. A sign chart tells you where a function is above the x-axis and below the x-axis. So that's the purpose of that. Great question. Okay, and the other ones. Excellent. So I'm going to skip net change theorem for a little bit. In brief, what it's trying to say, just for briefness, just because I want to focus on the next portion far more, is that when it comes to calculate, the definite integral, if you want to think of it in a real life sense, instead of just as a mathematical object, what it does is it computes the net change of a substance or a quantity that you're measuring. So the most common example is talking about velocity and specifically positions of functions, right? The antiderivative of velocity is the position. So if you take the antiderivative, if you take the definite integral of v of t, then what's going to happen is that's going to be the net change because you're going to get the position function. So people watching it, well, I can do it on this. Let's say you're walking along this line and then you decide to go backwards a little bit, right? And this is where you stop. The displacement, which is the integral of v of t, is just that pink area because that's how much you've been displaced. That's how, like, you started at 0, you went over to the store, and then you went back to your friend's house, and now you have only technically traveled 5 miles from your starting location. Whereas if I want total distance, I calculate all the way to the store and then all the way to my friend's house and add those two things up. So the absolute value is there because sometimes velocity is negative. If you're going backwards, if you're going back towards the house, then you're going to have a negative velocity because you're going backwards in the view of this this position function. So that's the thing to grasp for that one. So displacement, the net change of what you are, that's going to be calculating just how far you are from your starting point. Whereas if you do the absolute value, then you're finding actual total distance. So anyways, we'll if we have time, we'll go back to that. Otherwise, I want to get to this stuff. This is by far the most important thing. And it's a damn shame that we have to wait until the very, very end of the semester to go over it, because your Calc 2 professors will expect you to know this. They may be generous and maybe spend a day or two going over integral substitution briefly, but at the end of the day, it's going to be a lot of the onus is going to be on you. So just as a quick note about this, if you plan on taking Calc 2, if you plan on taking 182, you will thank yourself if you spend at least a few days before the semester starts, maybe the first couple days of the semester while things are still ramping up, to practice your integral substitution. You will be thankful that you did it. I can tell you it is going to be essential. So practicing it before the semester starts. I'll even send out, like, you have my videos. We'll have our videos on this that you can look over. There's also plenty of videos online and stuff. Please, please, please look at this before you take 182. You will thank yourself because instead of being starting a week behind, you're going to be starting ready to go. Okay? So the motivation for integral substitution is, the thing was with differentiation, I can give you guys any function and you can differentiate it. I can give you any combinations, and maybe it's tedious, maybe it's annoying as all get out, but you can take the derivative because of all the rules. But the problem with integration is it's not as cut and dry. Integration, there are certain functions that are integrable. They do have an antiderivative, but there's no way for us to compute them. We don't have any method that we've discovered that actually does them. And so that's what we're starting to do right now. This is the start of things that we'll go over in 182, which is the techniques of integration. The starting one being integral substitution. So as an example of this, 3x squared plus 2 times e to the x cubed plus 2x minus 5. Now, if I was just going to ask you to find the antiderivative of that, we'd be in a lot of trouble because, as we learned, you can't just take the antiderivative of pieces and then multiply them together, right? The integral of a product is not equal to the product of the integrals, right? We can't do that. So maybe we try and distribute it. Don't do this, but maybe we try and distribute this in. But even if you do that, you'll start to see that you have problems. However, now you might notice this, maybe you don't, and I wouldn't expect you to, at least not yet, is that if you take the derivative of e to the x cubed plus 2x minus 5 by the chain rule, we get e to the x cubed plus 2x minus 5 times 3x squared plus 2. That is to say that the integrand that we were given is the derivative of e to the x cubed plus 2x minus 5. So this integral would be the integral of d dx of e to the x cubed plus 2x minus 5 dx. And what we learned is that the antiderivative and the derivative are going to be inverse operations of each other, like the square root and the square, or the cubed root and the cubing power. So the integral and the derivative, they kind of cancel each other out. I guess I should say like that and that. It cancels both the d dx and the dx. And we end up with e to the x cubed plus 2x minus 5 plus a constant c. So just to recap real quick, because that does seem weird at first. The original integrand turns out to be the derivative of this function, e to the x cubed plus 2x minus 5. So instead of writing it as the integral of what I had originally, I can write it as the integral of the derivative of e to the x cubed plus 2x minus 5. The integral and the derivative cancel each other out, and we just get the function on the inside. Now that was nice and nifty, but how do I know how to do that in general? How do I know what to do in that case? You have a question?
Sorry, yeah, I'm going through a little. So is it basically saying like it's the derivative plus the 3x squared plus 2?
That was the second portion of the chain rule, yes.
Right. And that would be the same as the initial on the very first equation. That's the same as what was being multiplied. So they just cancel each other out.
Which thing are canceling each other out?
Like 3x squared plus 2. It's canceling each other out.
It's not canceling each other out. It's rewriting it as a derivative of a function so that we can cancel the integral symbol.
So the symbols just represent what it would give.
Yes.
Okay.
So the integral substitution rule. So some people call it integral substitution. Some people call it the substitution rule. Is that suppose g is a differentiable function whose range is an interval I, and let f be a continuous function on I with antiderivative capital F. That's a bunch of mathy talk. Specifically, it's saying, like, by saying that the range of g is I and f is defined on I, that just makes sure that the composition works. Because you need to be able to plug in values of g into the function f. So f needs to be defined on the range of g. That's what's going on there. That's just kind of crossing our T's and dotting our I's. If you decide to make u equal to g of x, then if you have f of g of x times g prime of x, you could rewrite that as f of u du, and the antiderivative of lowercase f is capital F, so it's equal to capital F of u plus c, which then replacing it in terms of x, we get capital F of g of x plus a constant c. Okay, that's a loaded theorem. What's more important to understand is how to use it. But what it is trying to say is to try and visualize it with differentials. I don't know why. This must have been there it is. Okay, cool. So we remember what we talked about briefly with differentials is if y is equal to f of x, then dy is equal to f prime of x dx. So basically, we're replacing this g prime Let me highlight it. We're no, 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 in green. We're replacing this g prime of x dx with a du. And we're replacing the the g of x with a u. Right. Da, 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 da. That's what we're doing. We're doing what we call substituting. We're substituting in u to make it fit nicely. Now, once you see practice, we'll start to get it. Now, all right. And I'm going to teach it my way. I'm not going to teach the term matching. I don't believe in it. So how do we do it? So we're looking at this one, and it's got x squared, 10x times x squared plus 1 to the 4th power. Now, as it currently stands, we could, if we really, 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 really wanted to, we could FOIL out x squared plus 1 4 times. X squared plus 1 times x squared plus 1 times x squared plus 1. And if you got your Pascal's triangle on lockdown, then that shouldn't be too terrible to do. But what if this was the 40th power? Right? Do you really want to FOIL it out 40 times? That seems highly impractical. So this is an example of where integral substitution makes things a lot easier. So what we're going to do, and this is going to look very, very strange at first. We're going to learn how to do this together. Well, I mean, I already know how to do it, so we're not going to learn it together. You guys are going to learn it together. But the point is, I'm going to go through this problem, and it's going to look weird at first. So what we're going to do is we're going to let u equal x squared plus 1. We're gonna basically create our new function u. U is a function of x, which we can do. That's totally allowed. And then what we're going to do is we're going to take the derivative. So, and leave a little bit of space up here, and then write, then the derivative of u, so du dx, would equal 2x. Right? Taking the derivative of x squared plus 1, that's going to be 2x. Now, here's where the hand-wavy math comes into play. And it's mainly meant to help us visualize things. Because remember, dy dx, or du dx in this case, is not a fraction, but sometimes can be viewed as a fraction to help us gather more information. That's kind of the goal of Leibniz's notation, is to understand that it is not a fraction, but sometimes can be viewed as a fraction. So what we're going to do is we're going to multiply both sides by quote unquote dx. I'm going to call this hand wavy math. Because once again, you cannot technically, like du dx is not technically a fraction, so we cannot technically multiply by dx. But if we could, what we get is that du is equal to 2x dx. Then what I want to do is I want to change the dx to a du. So I need to do what we call a, I'm going to solve for dx. So that gives us, we'll divide both sides by 2x and get that dx is equal to 1 over 2x du. This looks weird. Once again, believe me, I understand. We will get through it though. So a couple things, just because it does look a little bit weird when you're first looking at it. Notice that when I solve for dx, I now put the dx on the left-hand side. That's not required. If that freaks you out, you can definitely just flip-flop it. I know it's upside down, but like the idea is the same. So if you don't want to solve for the dx on the left-hand side, put it on the right-hand side, you're all good. But I get the dx by itself. So what I can do now is I can take this and I can replace dx with what it is in terms of u. So this is equal to the integral of 10x times u to the fourth times 1 over 2x du. To help visualize this a little more, I'm going to do some highlighting. The dx here is now a 1/2 x, a 1 over 2x du. All right. Yes, JT.
Is there a reason you don't just write it as du over 2x?
Excellent question. I was hoping someone would ask that. Is there a reason why I don't write it as du over 2x instead of 1 over 2x du? Now, the answer is that there is like plenty of textbooks will do this. Plenty of textbooks you see will do this. But I disagree because the du isn't really part of the integral. It's it's not part of the integrand is what I meant to say. Excuse me. It's not really part of it, so it should be treated as separate. That is my opinion. That being said, if you just write like that, du over 2x, you will get full credit because plenty of people do that. I'm just pretty particular about it, and I recognize that du is a differential. It's not actually part of the integrand, so it should not be treated as such. That's my thing about it, but it's okay if you want to. Yes.
So our last thing, where'd the u to the fourth come from?
Excellent question. So the u to the fourth is that x squared plus 2, we define that to be u. So I'm gonna maybe I'll even add that up here. Let's use what color haven't we used? We've used purple. Let's use blue. No, we've used blue. Orange, I guess. U equals x squared plus 1. So we're gonna replace it. All right. Now, big whoop, at least at first, but what you'll notice now is that what's nice is that the 10x and the 2x cancel, and we just left with a 5. So this is actually the integral of 5 u to the fourth du. All right. Now, if we look at that integral, the integral of 5u to the fourth du, that's an integral purely in terms of u. Remember, the variable, the du tells you what variable you're integrating with respect to. And that is a very quick integral. 5u to the fourth du is a very, very nice integral. That's just going to be equal to 5u to the fifth over 5 plus a constant c. That's u to the fifth plus c. But what's u? U equals x squared plus 1. So this is equal to x squared plus 1 to the fifth plus a constant c. If this looks like voodoo, I would understand that. It is somewhat of a little bit of voodoo, especially that hand-wavy math portion of it. So, do I write that on the next page? No. Okay. So then let's kind of go through this. Let's recap it one more time before moving onwards and talk about the step-by-step process. So, step 1. The first thing you need to do is choose a u. Choose a u to use for the substitution. And really, like, like I feel this way, and I think you guys would agree. I just want what's best for you. Right there. That's a great joke. That's not the joke, though. That's not the joke. That's not the joke. It's a good one, though. It's a good one. It's great. I do want what's best for you, and there are many different choices that will work in the long run. There are a couple things that will work over time that you can do multiple, but it would be the best thing. Now, I've got it on the next page. We'll decide what is a good choice for you, and your major, whatever you decide to be. Then what you're going to do, step 2, is find du equals blank dx and solve for dx. Step 3. So, step 2, you're really, like, technically speaking, we always skip this step right here. We skip the multiplying by dx. We usually just omit writing that because it's always going to happen. You're always going to find the derivative and then multiply by dx to try and get it into the proper format. So it's always going to be du equals the, let's say u prime. Let's write u prime here. Like that. And then solve for dx so that you can substitute it into the original. That's the next step. You're going to substitute it in, both u and dx. You're going to change dx to be what it is in terms of u, and then you're going to cancel. As long as you've done the correct integral substitution, everything should cancel out for the most part. There are going to be a few cases here and there that don't work out nicely, and we'll talk about them. But for the most part, if you make the correct u choice and you substitute in the original integral, it should be purely in terms of u. Once you do simplification, substituting the original formula, I should probably change this and say simplify and integrate. And then step 4, convert back to original variable. Typically x, but it could be y, it could be z, it could be anything you want. Okay? Any questions on that? That's the process. But you might be saying, like, once again, you're saying, well, I don't know what's best for you. Much like every parent ever. I don't know what's best. I can't plan for the future. I don't know how important AI is going to be. Yes, Parker.
Sorry, I know I'm sorry, but will there be a more concrete way to like find you?
To decide what choice of you is necessary?
Instead of using all that math.
So there is another way to do this, and it's called term matching. So regardless of what you do need to take the derivative of your u choice to figure out what needs to be matched. So the other way to do this real quick, if you want to add this to your notes, you can. So alternative is what we call term matching. Now, the reason why I don't like term matching is because sometimes what you have to do is a lot of sneaky algebra that's kind of annoying, kind of clever. But looking at this one, we had the integral of 10x times x squared plus 1 to the 4th dx. Then what you'd want to do is you'd make u equal to x squared plus 1. Sorry, let me actually. U is equal to g of x, which is equal to x squared plus 1. So that means that f composed of g of x is equal to, oh, no. Sorry. I just do not like this method for a myriad of reasons, but let's go through it. So your function is x to the fourth, so that f of g of x is equal to x to the second power plus 1 to the fourth power. But furthermore, g prime of x is equal to 2x. So it's very, very weird to do this way. We'll explain what's going on a little bit more in just a moment. But this means that f of g of x times g prime of x is equal to x to the fourth plus 1, x squared, excuse me, the fourth power times 2x. Okay, so what we're trying, the whole point of this situation is to try and figure out what the original function is, lowercase f, what function is being input, is going to be substituted into f, in this case, x squared plus 1. And then what you're going to do is look at your integrand and say, okay, is there a way I can get a 2x out of a 10x? And yes, there is. 10x is technically 5 times 2x. So when we have it, we have the integral of 10x times x squared plus 1 to the fourth dx. You're going to rewrite this as the integral of 5 times x squared plus 1 to the fourth times 2x dx. Right here, this is f prime of, sorry, not f prime. This is f of g of x times g prime of x dx. And 5 is just a constant, so it can be ignored. It can just be brought out front. And so we have the integral of 5 times the integral of u to the fourth du by the integration rule, by the integral substitution rule. And then we go from there. 5u to the fifth over 5 plus a constant c, which ends up being x squared plus 1 to the fifth power plus a constant c. So the difference between my method and this method is term matching requires you to say, okay, how can I get my derivative of my inside function from the thing that's not inside my function, essentially? And it works a lot of the times, but sometimes it doesn't work as nicely. And what we like by doing this other method instead, you kind of take care of doing that little bit of trying to counterbalance the weights that you've been putting off. So like this time you're like, okay, how do I break up a 10x into a 2x and something else? What if it was an 11x? How do you get a 2x from 11? Quite naturally, you write it as 11 over 2 times 2x. Haha, little cheat. That's how you break it down. So there is a way to do it, but it requires being a little bit silly and clever and using a little bit of excess algebra that we don't need to. Instead, by doing it this way, it kind of bypasses you trying to figure out that matching. Like, how do I break down a 10x into a 2x and something else? Wow, this thing is really laggy today. This basically takes care of that for you. So this method, in my opinion, and most students will agree, is the far superior method. And I'll show you the shorthand way in just a moment. So there's going to be a much more efficient way. We don't have to write let u equal blank, and we don't have to write du dx equals 2x and multiply by dx. We don't have to do that. So, but the natural choice, the thing you might be wondering is, well, how do I know what do I choose for you? And the answer is mess around. Really, there is no way, there is no better teacher than practice. Just like if you're trying to learn how to take care of a home or something like that. If you're trying to learn how to use your toolkit, you get better by using the different tools. That's the only way to get to it. And in certain circumstances, you'll start looking at a problem in your house and saying, oh, well, that requires a hammer, or I'm going to need a wrench for that problem. That problem has to do with my sink. I'm going to need to use my plumbing tools. That problem has to do with a leak in the roof. I'm definitely going to need to have some I don't know how to fix a roof, but if you get the idea, something like that. Or I have a broken piece of tile. I need to break it up. I need to use my hammer to kind of chip that piece away with the screwdriver, whatever it may be. But that being said, there are certain things that you learn with time, and those ones are to first and foremost try and pick something on the inside of a large or weird power or inside of a radical. So with this one, the integral of 4x minus 3 times the 7th root of 2x squared minus 3x plus 5. A perfect choice for you would be the inside of the radical. U equals 2x squared minus 3x plus 5, which implies that du is equal to 4x minus 3 times dx. The entire thing times dx. A very classic mistake that students will make is they'll forget the parentheses. But remember the hand wavy math. We multiplied both sides by dx. So we're multiplying the entire thing by dx. And then we'd solve for dx. We'd get dx is equal to 1 over 4x minus 3 times du. So dx now. So I divided both sides by 4x minus 3. So you can write it as du over 4x minus 3 if you want. I don't like doing that because it just hurts my soul a little bit. So that's a good choice of u, something on the inside of a radical or a large power. Another example, if we have sine y times the quantity cosine y minus 3 to the pi, that's something inside of a large or weird power. Pi is a weird power. So we'll make u equal to cosine of y minus 3. That would imply that du is equal to negative sine of y dy. So that dy, when we solve for it, it's negative 1 over sine y du. So the convention is to write the dy on the original variable. So in the original one dx, this one dy or whatever, right on the left, and write the du portion on the right hand side. So I divided both sides by negative sine u. That's why we got negative 1 over sine u. I mean, you could write it as 1 over negative sine of y if you wanted to. It's not that big of a deal. But either way. The next type of thing is something inside a denominator, but sometimes in conjunction with option 1. So with this one, 16b minus 4 over 4b squared minus 2b plus 3. The best choice for you would be the denominator. So we'd make u equal to 4b squared minus 2b plus 3, the entire denominator. So that would mean that du is equal to 8b minus 2 du. John Doe student writes that. Why is John Doe student wrong? Yeah, he's right. Parentheses. Because if you don't write the parentheses, you might think that you need to subtract 8b to solve for du. There should only ever really be division or multiplication when it comes to solving for b. Why did db, sorry. Not du, db. That means that db is equal to 1 over 8b minus 2 du. Apologies. So parentheses, parentheses, parentheses. I trust you to do it without the parentheses, but I don't trust your environment. Someone could be sneezing while you're writing things. and you might just get distracted just enough to forget to divide. The next one. So the next example is a perfect example of something in the denominator in conjunction with a large or weird power. The denominator is z to the third plus z to the fourth, all raised to the fifth. But if you make it u equals the whole thing, if you make u equal to, so don't write this down. If you make it equal to this, the entire thing, it won't work out nicely. There might be a way, there may be a way to fix it, but it would be really, really algebra tricky and unnecessary. Instead, you just make it to the inside of the weird power that's in the denominator. That would mean that du is equal to 3z squared, parentheses 3z squared plus 4z to the third, dz, which implies that dz is equal to 1 over 3z squared plus 4z cubed du. So right now we're just trying to figure out what we should properly choose for u. That's what this page is all about, trying to show you the right choices. Because when it comes to the exam time, because I guarantee you, I would not be surprised. In fact, I'd be shocked if it wasn't on there. There's probably going to be at least one integral substitution problem on the exam, on the final. So what I will tell you is if you at least choose the correct u and find the correct du equals blank dz or dx or whatever it may be, I will give you at least like 2 points on the exam. So even if you can't finish the problem, you can still get a little bit of partial credit by knowing what you're supposed to start off with. The last type of situation that we're going to encounter in this course, at least for now, is to try and do something on the inside of a function, like e to the box or tangent of the box or natural log of box or whatever. You're going to make u equal to the box. So in this case, 27 secant squared theta e to the tangent theta d theta. The best thing to do would be to make u equal to tangent theta. In a weird way, you can actually make u equal to e to the tangent theta, and that does work, but it requires being very, very clever. Maybe if we have time, we'll talk about it. But this would mean that du is equal to secant squared of theta d theta. So solving for d theta, that'll be equal to 1 over secant squared theta du. And so with all of these ones, by the way, once we finish them, I'm going to talk about them. Last one, sine of the third root of x, which, by the way, once again, this is x to the 1/3 power. And this is x to the 2/3 power down below. We could write it as x to the negative 2/3 and put it up top, but that's actually going to be that's not going to help us as much. It'll still work out, but regardless. So u is equal to x to the 1/3 power. It's something on the inside of a function. It's inside the sine function. So then du would be equal to x to 1/3 x to the negative 2/3 du or dx, excuse me. So this one is a little bit weirder than the other because x to the negative 2/3 is, I mean, you can divide both sides. Yes, I'm aware, even though it hasn't showed up yet. Okay. And we'll talk about the image there in just a moment. It's important. It's a very, very important one. But anyways, you can write this. That means that dx is equal to 3 over x to the negative 2/3 du. Let's take a second to understand what's going on there for a quick moment. So I'm dividing by 1/3. So if I want to solve for dx, I need to multiply by 3 to cancel out that 1/3. That's why there's a 3 up in the numerator. And then I'm dividing by x to the negative 2/3, which is why it's like that. Or you could write it as, or dx is equal to 3x to the 2/3 du. So maybe we'll even add one more step. Actually, we'll add one more step, so maybe this will make it a little more clear how this came to be. So this would mean that dx is equal to 1 over 1/3 x to the negative 2/3 du. All right, so let's recap that real quick. So solving for dx, I'm going to divide both sides by 1/3 x to the negative 2/3. You're dividing by a fraction 1/3, so you flip and multiply. That's why it's now 3 over x to the negative 2/3. But x to the negative 2/3 is really 1 over x to the 2/3, so that flips it up and gets us there. That's the algebra needed for that problem. So the key to success, though, 100% in this course, and especially in Math 182, is to keep trying. It doesn't matter if you're wrong. Just erase it and try again. My recommendation, by the way, when it comes to the exam on these types of problems, is if you are getting stumped, try it on new paper. Do not look at the old paper at all. Do not do that. You will keep getting yourself in the same cycle because you'll want to believe that your original work is correct when it might not be. So try it again with a fresh start. Do not look at your old work. It'll confuse you. That's my recommendation. Take it from my experience from me messing up many times in mathematics by looking at old work thinking it was correct. So try, like if you get stumped, try again and try something ridiculous. If something doesn't work, try something that you've never tried before. Worst case scenario is it doesn't work. Best case scenario, you figure it out and you get the credit, right? So hang in there. Keep trying. Be like this little cat, all right? What I want to go back, so we've solved for dx each time, or d theta or dy or whatever it may be. Notice that if I were to replace dx in this situation with this, do you notice that the 4x minus 3's would cancel? And this would no longer be that. It would be u to the 1/7. So I've really just got u to the 1/7 du, and that is an integral that we know how to do with the power rule. Similarly with the next one. If I were to do this, if I were to replace dy with what it is, dy is equal to negative 1 over sine y du. Replacing dy with what it is, the sine y's would cancel. Cosine y minus 3 is u. So we've got that these cancel. This negative 1 sticks around, and this is u to the pi. And that is something we can integrate. U to the pi, the integral of that would be u to the pi plus 1 over pi plus 1. Same thing here, but slightly differently. If I were to replace the dB with 1 over 8b minus 2, this is the reason why I don't like term matching, is this allows us to figure out how to cancel these things. 16b minus 4 and 8b minus 2, they don't necessarily cancel right off the bat. But if you realize that if you factor out a 2, then you can cancel these things out, and it works out. So we will see that in just a moment. But that's what's happening. Every single time, basically, everything should cancel out, and it should be purely in terms of u once you finish it off. So let's go ahead and work through some problems, okay? So looking at this one, the integral of 1 over the square root of 2t plus 3 cubed. What would be a good choice for you? The whole denominator or the 2t plus 3? Just the 2t plus 3, correct. Because you can think about it. So we wouldn't want to use u equals 2t plus 3. Don't write this down. This is not correct. You don't want to do that one. And I want to show you why. So this is what would happen. This is why we don't want to do that. Well, then du would equal 3 times 2t plus 3 to the second power times 2 dt. And do you notice how there's no, in this problem right here, there is no 2t plus 3 squared. There's a 2t plus 3 squared, but it's inside of a square root. It won't cancel nicely. So instead, what we will do is, as Jose suggested, we will make u equal to 2t plus 3. Then du would equal 2 dt. The derivative of 2t plus 3 is just 2. So to solve for dt is going to equal 1/2 du. So I'm going to stop writing this after this one. Maybe I'll do it one more time, but regardless, I'm going to take dt and replace it with 1/2 du, because I've just claimed with my hand wavy math a little bit that dt is equivalent to 1/2 du. Substitute that in, and we get the integral of 1 over u to the 3/2 times 1/2 du. Remember, we have the square root of something cubed. That's the same thing as the 3/2 power. Now, in its current format, that's something we don't really know how to work with, but there's not a problem here. We can convert it by writing it with a negative exponent. So this is equal to the integral of 1/2 u to the negative 3/2 du. Your integrals should always have, once you've done the simplification, there should be no more of your original variable. There's no more t's, right? No more t's. We're good. And so we can integrate that now. We totally can. That's going to be 1/2 u to the negative 1/2 over negative 1/2 plus a constant c. Then, is everyone okay with that? Any questions on that integration? Parker.
How did you get the integral of 1 over u to the 3/2 of eventually
From here to here?
yeah.
Sure. So u is declared to be 2t plus 3. And then this right here, that is equivalent to 1 over 2t plus 3 to the 3/2. Because it's the third power, power goes above, root goes below. So that's converting it to from radical form to exponential form. U is declared to be 2t plus 3, so that's why I've replaced it with a u. And then dt, from our work here, dt is equal to 1/2 du. So I'm going to replace the dt with a 1/2 du. Yes. Then we do the power rule. Yeah, Jose?
Before we continue, you said to like, when you're declaring u to like mess around. What would happen if we just like did the numerator instead?
Well, then, so excellent question. Let's see what would happen in just a moment. And we'll talk about that. So here, the 1/2 would cancel. We'd still have that negative sign, so we get negative u to the negative 1/2. U is declared to be 2t plus 3, the 1/2 plus a constant c. You could write it as negative 1 over the square root of 2t plus 3 if you really wanted to, but this is fine. You'll know when to convert it back because you dropped the integral sign. You have integrated it. So you've taken care of the major problem. That's when we go back to, in terms of our original variable, in this case, t. Once we've integrated it and we've actually taken care of the integral symbol, that's when we need to take our little, we need to go backwards and convert it. Don't do it any bit before that at all. So what would happen if we had made u equal to 1, the numerator? Well, then du would be equal to 0 dt, and there would be no way to solve. We can't solve for dt. We'd be dividing by 0, and that would be problematic. JT, yes.
I'm sorry, what happened from the, on the far right, 1/2 u to the negative 3/2 power? How did that go from that to what's under?
From here to here?
Yeah.
Anybody know? The antiderivative. The antiderivative, like this is purely in terms of u, so you can find it by the power rule. It becomes negative u to the negative 3/2 plus an additional 1 over negative 3/2 plus 1. So yeah, let's go ahead and add that as a little note. It's negative 3/2 plus 1 equals negative 1/2. That's where that's coming from, by the power rule. Okay. Next one. The third, y to the third power times the square root of y to the fourth plus 2. What would be a good choice for you?
Y to the fourth plus 2.
Exactly right. Couldn't have said it better myself. That's a good choice. Y to the fourth plus 2. So we're going to make u equal y to the fourth plus 2 so that du is equal to 4y cubed dy. Taking the derivative of that u value would be du dx is equal to 4u cubed, quote unquote, multiply by dy, even though we technically can't, but we can if we want to visualize it. And then we'll solve for dy. dy is equal to 1 over 4y cubed du. So this becomes the integral of y cubed times the square root of u times 1 over 4y cubed du. And the y cubeds cancel. And remember that u to the square root of u is u to the 1/2. So this is equal to the integral of 1/4 u to the 1/2 du. And that is purely in terms of u. Now that we've done the simplification that we've done in blue, there are no more y's in our integrand. That's a good thing. If no more y's show up, that's good news. That means that you have written it as a substitution, that you've substituted in that variable and gotten rid of anything that had the original variable in it. And then we can use the power rule. This becomes 1/4 u to the 3/2 over 3/2 plus a constant c. Flip and multiply. So you're going to multiply by 2/3. 2 and 4 cancel a little bit. This is 1/6 times u, which is y to the fourth plus 2 to the 3/2 plus a constant c. Now, any questions on that? Yes.
Could you do y to the fourth plus 2 to the 3/2 over 6
Yes, that would be fine too.
plus c?
Yeah, plus our constant, our consistency. Here's the cool thing. As a reminder, you can check your work by differentiating. Your answer. I guarantee you, if you go through and you take the derivative of this thing, right, by the chain rule, 1/6 times 3/2, that becomes 1/4. Then you got the derivative of the inside. So that'd be 4y cubed. The 4 and the 1/4 cancel. You get y cubed on the outside times y squared plus y to the fourth plus 2 to the 1/2 power. It works. Now there are certain few circumstances where taking the derivative, it doesn't look the same, but that's few and far between. Basically, almost everything we do, if you take the derivative, it should get you back to the integrand because they're inverse operations of each other. So you can always be certain of your work if you check. All right. We're going to do...
I think it 1/6. You said you simplify and then.
So I did 1/4 divided by 3/2. Or the way I did it is I said, well, I'm divided by 3/2. That's the same thing as multiplying by 2/3. And I did 1/4 times 2/3.
So you did the multiplication and then substitute.
Yes, at the same time.
So it would have, if you had an intermediate step, it would have been u to the 3/2 over 6.
Yes. Yes.
Okay.
Mhm. All right. Any other questions? Okay. I know you guys are ready for that joke, aren't you? You're so ready for it. Ooh, that's a good question. Got 12 minutes. We're gonna need to do it like we'll see. We'll see. We'll see if we can get it today, or we'll have to wait until the very last day of class. I'm building it up for that long. All right. So this one, what should you be? Remember, Soldier Boy. Chandler, you're in the Soldier Boy. What should you be?
You.
Yes. You should be what? I don't know. I can't do math. Mark. The numerator? Let's see what happens. If u is equal to 6x squared plus 8x minus 10. So I'm writing in red. I'm sorry, it's not the right choice, but I want to go down the path and see what happens. Then du would equal 12x plus 8 dx. So dx would equal 1 over 12x plus 8 du. And this would become the integral of u over x cubed plus 2x squared minus 5x plus 6 times 1 over 2x plus, or 12x plus 8 du. And nothing's going to cancel, right? We actually end up having a more complicated denominator. So that doesn't work out. That's okay. We just go back to the drawing board. We take our tablet and we delete that and we go good. Or we use our eraser, one of the two. Parker, did you have an idea?
It should be the denominator.
The denominator instead. Let's see what happens. U equals x cubed plus 2x squared minus 5x plus 6. Then du would equal parentheses, because remember, we're going to be multiplying both sides, technically speaking, by dx. So the entire derivative needs to be multiplied by dx. It'd be 3x squared plus 4x minus 5 dx. So that dx is equal to 1 over 3x squared plus 4x minus 5 du. We're solving for dx every time. We're solving for the original variable's differential. So substituting that into the equation, let's see what happens. This equals the integral of 6x squared plus 8x minus 10, all divided by u. We declared that the denominator was equal to u, so we just get to write a u in its place. And then multiplied by dx, but we just solved for dx down below. Dx is equal to 1 over 3x squared plus 4x minus 5 du. And you might be panicking, saying, well, Phil, that doesn't cancel. It does. It does. You can factor out a 2 from the numerator. This is equal to 2 times the quantity 3x squared plus 4x minus 5. And lo and behold, those would be able to cancel. Now, the interesting question would be, what if this was instead of 3x squared plus 4x minus 5, what if it was 3x squared plus 4x minus 4? What would we do then? How would we take care of it? And that's a tough question. There are ways to get around it, but it takes a lot of practice. Things that you'll learn in Math 182. You'll learn more and more tricks as we go along. But regardless, that does cancel that for us. Now we have the integral of 2 over u du, which is really 2 times 1 over u. So what's the antiderivative of 1 over u? Natural log of the absolute value of u. So this is equal to 2 natural log of the absolute value of u plus a constant c. So that'll equal 2 natural log of the absolute value of x cubed plus 2x squared minus 5x plus 6 plus a constant c. A general constant c. Okay? All right, next one, unless there's any questions on that. So pick your u, find du dx, and multiply by dx, which we do in all one step, right? Du equals the derivative times dx. Solve for dx so that you can substitute in the equation. Cancel everything that you can. There are a few cases where this is not the case. We'll talk about those soon. It should be the case that almost everything goes away. Most of like 99% of the time, everything should go away and you should have purely something in terms of u, like this, 2 over u du. No x's in there at all. And we integrate. And then once we've integrated, we've dropped the integral symbol, much like when we take the limit, we drop the limit symbol. And then we've got this thing, but we want to write that in terms of x. So there's we have it. Next one. What should u be? The tough one, because there's not really a weird power. There is. So what would happen if we did sine squared? Sadly, it's not going to work. But if we were, u equals sine squared of x. Or theta. So this is not correct. I should be writing in a different color. Then we get 2 sine theta cosine theta d theta. So d theta would equal 1 over 2 sine theta cosine theta du. So this would equal the integral of u squared, or u times cosine of theta times 1 over 2 sine theta cosine theta du. And you'll see the problem. The cosine thetas cancel. Yeah, that's awesome. The cosine thetas do cancel. But we have a 2 sine theta in the denominator that doesn't cancel. So our integrand now has u and it has sine theta. Now there is a small way to kind of combat that. There's a thing that I like to call reverse engineered u substitution, which we'll talk about next time, that will bypass that. But for now, we can't really do that.
You do just sine of x.
U is just sine of x. So that is the correct choice. And the reason for that is it's something inside of a power. Remember that this is the same thing as sine of theta to the second power. It's the thing that's inside a weird or large power. It's not a large power, but it is a large power in comparison. So u is equal to sine of theta. That would mean that du is equal to cosine theta d theta. Solve for d theta, solve for your original variables differential. So d theta would equal 1 over cosine of theta du. And it's not going to be necessary on this one, but please keep in mind that sometimes you might need to use your trig identities. 1 over cosine u, that's secant. Well, 1 over cosine theta is secant theta. That might show up. Maybe it does, maybe it doesn't. But know that you can use trig to your advantage every once in a while. So this becomes the integral of u squared cosine theta times 1 over cosine theta du. And the cosine thetas cancel. And we have the integral of u squared du. If you want to skip rewriting it, and like if you're okay having all the things be canceled and being able to find the integral of u squared right there, be my guest. I just like seeing it pretty and making sure that everything's been gone and removed, but that's just me. Integral of u squared by the power rule would be u to the third power over 3 plus a constant c. I have integrated. I've dropped the integral sign. So I can then replace u with what it was claimed to be, which is sine of theta. So sine of theta cubed. Sine cubed of theta, more specifically, over 3 plus our constant c. Boom. And I guarantee you, if you take the derivative of that, you will get back the integrand. Good way to check your work. Okay. What I will so we don't have enough time to go over any other ones. I'm going to tell you, tomorrow's Wednesday's quiz, it will be one of these two problems. One of these two ones. So make sure you figure them out. Okay? Be ready. Free, easy 10 points. You know what to do. Just make sure what's best for you. So we'll start up next time with the joke. It'll be great. All right, guys. That'll do it for today. If you guys have any questions, feel free to email me. Otherwise, you guys have a great rest of your day. Keep your nose to the grindstone. We only have 1 week left before finals. I know we want to walk because we had a nice Thanksgiving and we all had a good time. It's not the time to let up. Just keep pushing through it. It'll be done soon. All right. Have a great rest of your day. And if you